Hi everybody, welcome to this new module about architecting and design. Apparently today I'm alone here in the room, so, well, by the way, I'm gonna streaming. So today lecture about design for quality. We start now our journey in design, and then we're going to discuss what the design is and what we are supposed to do when designing. And very important, we're going to stress how to make good design for improving the quality of our software system. Okay, so let's move on then. Design for quality. So let's recap first of all what is quality. Quality is defined as the degree to which a system, component, process meets the specified requirements or the customer's need or the expectation. Okay, this is a definition from the IEEE standards 610. This is quite problematical, and where is it? For software system, because there is always a tension between the customer quality requirements and the developer quality requirements. You remember during our first lecture we discussed how quality is in the eye of the beholder. So we have many stakeholders that are involved in the software development process, and each of them has a different perspective on what quality is and what are the quality attributes relevant for the product. Okay, usually quality requirements are really difficult to specify in an ambiguous way. So sometimes people say, okay, I want a user interface which is modern. Okay, well, what does it mean? I mean, in order to be able to specify these quality requirements, we need quality attributes that must be measured. Okay, so otherwise, if we cannot measure the quality, so it's quite impossible to specify correctly what is the level of quality that we want to achieve. Usually software specifications are incomplete and often inconsistent. Okay, you remember we discussed and you also seen in the requirement engineering module how much difficult it is to interact with the customer and let the customer clearly express their requirements. Okay, and when talking about quality, it is even more difficult. So then the focus in this sense should be on the fitness for purpose rather than on the specification conformance. Okay, so the system should meet the needs of the users. Then we need to understand what are these needs. And in order to understand what are these needs, we just need to answer, well, few questions. So first of all, should us ask ourselves if the software has been properly tested. Okay, how many tests did you run? What are the results that you gather from the results? And then if the test will cover all the possible inputs and output of the software. Then we should ask ourselves if the software has been sufficiently dependable to be used in every day. Okay, I mean, just think about your users that keep working with the crashing software. They get mad in a while. And then about the performance. So is the performance of the software acceptable for normal use? I mean, still, if I need 5 minutes to accomplish and perform an operation, so I get mad. So the software should be performed. Okay, I don't want to wait too much time in order to do easy things. And then, is the software usable? How much easy is to use the software? Okay, is the software well structured and understandable? That's very important things. That's more in the eyes of the developer, and that this is the topic that we're going to discuss deeply today and next week. Okay, well, and Friday, of course. And then for the programmer side, have the programming and documentation standard been followed in the development process? This is also very important and something that we're going to discuss later on. So, first let's start discussing better and more about quality. And in order to do that, we start discussing the software quality model. Okay, this is also a standard issued by ISO 25010, which is a software product quality model. It's very important. I mean, if you want to be if you want to get accepted and be certified, you have to follow the standard. So this quality model describes many different qualities that we should be able to fulfill with our software. We will not discuss all of them, but only few of them. And in particular, we're going to discuss about functional suitability. That, I mean, which means functional completeness, correctness, and appropriateness, something that you already discussed during in the requirement engineering module. Then we have performance efficiency, time behavior, resource utilization, capacity, something that you already discussed and learned in the performance engineering module. And finally, we're going to talk about the maintainability in this module. In particular, we're going to discuss about modularity, which is very important, what is modularity, why it is important, and how to achieve it. Reusability, analyzability, modifiability, and testability. Okay, these are very important quality attributes that we will discuss during this the last module. This doesn't mean that all the other quality attributes are not important, but I mean, we cannot cover everything and then decide to cover the most important, the ones that we consider very important, okay, for this course, which is about design. So, functional suitability, I'll go very quick on this because I said you already discussed these qualities during the requirement engineering module. So we have functional completeness, which is the degree to which the set of functions covers all the specified tasks and user objectives. I mean, you have your requirements and then you implement your software, and then you have to check if all the requirements that you stated during the requirement engineering phase are met and has been implemented in the software. Then you have functional correctness, which is the degree to which a product or system provides the correct result with the needed degree of precision. I mean, that's mostly concern testing. You run the test, and then if the output of your software is compliant with the one expected, then it's good. And finally, we have functional appropriateness, which is the degree to which the functions facilitate the accomplishment of specified tasks and objectives. Okay, and this is usually when you have beta testing. Okay, you let the users to work with the system and see if the functions that you're providing with the software help the users in doing their job. Then we have performance efficiency. Also go very quick on this. This is composed of the different sub-characteristics, which is time behavior, which is the degree to which the response and processing times and throughput rates of a product or system. Okay, when performing these functions, and if these meet the requirements, then you have to measure the response time, processing time, and throughput. Okay, if these measurements meet your expectation, then you're okay. If not, then maybe you need to revise the design and the implementation of the software. Then the resource utilization, which measure the degree to which the amounts and types of resources used by a product or a system when performing its function meet the requirements. I mean, if you consume and use too much RAM or too much space on your hard drive, then you might face an issue, and then you need to revise, I don't know, your database, for example, because you are not storing properly your data. And then finally we have the capacity, which is the degree to which the maximum limits of a product or system parameter meet the requirements. Okay, so you have to check when you will consume all the resources that you have available. And then we have maintainability, okay, which represent the degree of effectiveness and efficiency with which the product or the system that you are building can be modified in order to improve it, correct or adapt it to changes in the environment, in the requirements. Okay, we already introduced these problems. So world is changing and it evolves. And the environment evolves, and also the users evolves. And then together with them, also the requirements for your application might evolve. I mean, you change your execution environment, then you need to evolve the application accordingly, because otherwise it might not work anymore on the new system. For example, you upgrade your operating system, and then you also have to upgrade the application, the software, in order to work in the new operating system. Okay, but also the users can change. They evolve. They have new requirements, and then they want to have new functionalities. So then maintainability measure how much easy is to change your software in order to adapt to the new to the environment, or how much easy is to add or modify functionalities in order to meet the new requirements posed by the users. In order to understand how much maintainable is the system, we need to deal with some sub-characteristics. Modularity is very important. It measures the degree to which a system or computer program is composed of discrete components, such that a change to one component has minimal impact on the other components. Okay, the more autonomous these components are, the easy is to make change in such component, because this means that the change that you are making the component does not affect other parts of your system. Okay, that's very important. And then, as we will see, we're going to discuss about single responsibility principle, which is very important for this purpose. Then we have reusability, which is the degree to which an asset can be reused in more than one system or in building other assets. I mean, this means whenever you invent the wheel, so you don't want to reinvent the wheel every time you need it. Okay, you want to invent the wheel once and then reuse it many times. Okay, this does not come for free, and this does not come by chance, but must be designed. Okay, the modules should be designed in order to be reused. And then we have analyzability, which is the degree of effectiveness and efficiency with which it is possible to assess the impact on a product or system of an intended change. Okay, so how much does it cost to make a change in one component? Does this change affect other components within the system? Will this change cause failures somewhere else? Then you need, in this case, you also need to, you might need to retest all the system. And then we have a modifiability, which is the degree to which a product or system can be effectively and efficiently modified without introducing defects or degrading the existing product quality. Okay, so how much easy is to modify a given product? Okay, that's very important, and then we will discuss this later. So modularity, reusability, analyzability, modifiability are very important for this course in order to understand how to design software that are modular, reusable, easy to change. And then we have testability. Okay, we don't go in deep into testability, as you already had a course about testing. Then you should know how to test a given software. Okay, but by the way, this measures the degree of effectiveness and efficiency with which test criteria can be established for a system. Okay, product or component, and tests can be performed to determine whether those criteria have been met or not. So let's then go deep into the design process and see how we can design software that achieve and have a good level of quality, okay, according to this model. First of all, what is design? So design means problem solving. Okay, it's a problem solving process whose objective is first to implement the system functional requirements. I mean, your customer is asking for a specific functionality, then you have to provide him with this functionality. Otherwise, you're not meeting his requirements. Okay, and then you also have to respect the constraints that have been imposed by quality, platform, process requirements. Okay, well, including the budget. And this is something that we already discussed a bit at the beginning of this course when we discussed what is software engineering, what is design. But now it's very important. So design is a problem solving. We need to solve the problem stated by our customers. Okay? And the problem stated by our customer is described and specified in the requirement specification. Then once we have the requirement specification, we have the problem. Then we can start designing, then solving the problem stated by the customer. And then, of course, we want to adhere to general principles of good quality. Okay, and then this is what we're going to discuss today. What are these principles and why they are important? So, we are designer, and usually a designer is faced with a series of design issues. Okay, What is a design issue? Design issue is a sub-problem of the overall design problem. So we have the set of requirements stated by our customer, then we need to solve this problem. Okay? Then we can divide this big problem in a set of sub-problems which are smaller, and then that we can address in isolation. Okay? So each issue normally has several alternative solutions, and these solutions are called design options. Okay? Our goal as designer is to, well, make a design decision and resolve each single issue in isolation. Okay, and then put together all these solutions in order to provide the final product. And this is used called the divide and conquer methodology. Okay, we have a big problem, we split the big problem into a set of small problems, then we solve the set of small problems, and then we put together this set of solutions in order to solve the big problem. Okay. This process involves choosing the best option from among all the alternatives. Okay? For every single problem, we will state and list well, a set of different alternatives, and then we have to pick the best option. And this is really, really challenging. Okay? So how to do that? Start to use your knowledge. Okay, and what is your knowledge? First of all, the requirements. If we don't have requirements, we don't have a problem. We don't have a problem, we don't need solution. Then always start from the requirements. Okay, that's very, very important, and I will always keep stressing this point. Okay, making good requirements is required in order to find a good solution. Okay. So then start from the requirements, and then consider all the design that's been created so far. I mean, we are talking about well-known design, for example, design patterns, architectural patterns. I mean, all that solutions that have been proved to work. Okay, we need to use our knowledge. Okay. Then, of course, we need to use the technology available. We need to pick the right technology according to the set of specific requirements that we want to solve. Okay, we cannot use a given technology just because we like that technology. We need to properly choose the technology according to the specific problem that we want to solve. Okay, some technologies are very good for the problem we want to solve. Some other technologies are very bad because they impose some limits to our solutions. And then remember always to use software design principle and best practices. They are called best practices because they work. And then we talk about this, so we will discuss now about design principles and best practices. There are a bunch of principles and best practices, and each of them will provide you some interesting properties. And then we have to keep in mind these properties. Okay? So whenever we need a given properties, then we know what is the design principle and the best practice that we have to apply. And finally, what has worked well in the past? I mean, use your own experience. If you already implemented something and it worked well, you need to reuse. That's why reusability is another really important property. I mean, the more reusable are the so the good solution, the better. Okay, you save money, you save time, you save development and design effort. But what if the knowledge is incomplete? So what if you are facing a new problem, something that has not been faced before? Well, design is a creative process. Okay, we can reuse our knowledge, but we might also reuse our knowledge in a creative way. Okay, try to think out of the box. Okay, and then when alternatives are not obvious, you just need to be creative and push the boundaries. Okay, that's something that we cannot teach. It's up to you. It's up to you, your creativity and how smart you are. We cannot teach to you how to be creative, but we can teach you how to use your knowledge and best practices, design principles, technology, design, and so on and so forth, in order to, as a base for your creative process. Okay. So, let's start discussing. So we say that we need to list for every single issue, we need to list a list of design options, and then we need to pick the best option. So the set of all possible designs that could be achieved by choosing different alternatives is called design space. So what is it, a design space? Let's see. Let's suppose we have a starting point. Okay, we need to create a design for our application. So the first choice might be, should we create a client-server application, or should we go for a monolithic design? Then we will see later on what are these two. I mean, there are two different architectural styles. So what is the structure that we want to give to our software? So shall we go for client server, or shall we go for the monolithic one? Then let's suppose we make first choice and say, okay, let's go for the client server, because client server has good properties that we will discuss later. Okay, once we have the client server, then we pick this option because we think or we measure it's better than the monolithic one. Then we now face another choice. Should we go for a fat client or for a thin client? That's something that also we're going to discuss later on. Then let's suppose we choose the thin client, and then then we have another choice we have to make. So should we separate the user interface layer from the client or no, separate the user interface layer for client? So what should we do? Should we have a separate user interface or no separate user interface? Then we pick a new one, and then finally the last choice. Should we go for Java, Visual Basic, C++, or maybe Python or whatever? And then here we talk about the technology, and then we have to choose the right technology according to the requirements for our software. Okay, for example, let's suppose that interoperability is very important for us, because we want to develop once and run the software on over many different platforms. Then we pick the Java, because Java is very nice for this interoperability. So this is the red one that you see here is called design path. Okay, that's the path, the journey that we make through the design space. Okay, we have design space with all possible different designs that we could choose, and then we make a path through this space. Okay. All these red dots represent a design decision that we as a designer made during our journey. That's very important. All these decisions must be recorded, okay, along with the reasoning that went into making them. So you have step by step, you have to list all the different options and then justify and make reasoning and why you picked, for example, the client server instead of the monolithic software architecture, or why you prefer the thin client option with respect the fat client, and so on and so forth. Okay, then you must clearly list all the possibilities, make a choice according to some criteria, and then explain and record why you made this specific choice. So, and then the entire record of decision becomes your design document. Okay, and that's very important, because then once you have this design document, you provide this design document to the developers, and then the developers will use this design document to implement the system itself. Okay, that's very important. It's the starting point for the last phase of the software development process. So there are two different ways to make to run this process. One is top down, and the other one is bottom up. Okay, let's start with top down design. First, start designing the very high level structure of the system that we will call software architecture, and then we will discuss extensively about this in the next lecture, because this is very important. Okay, it's the first point. Design the structure that you want to give to your system. The better the structure that you give to your system, the better will be the system. Then it's very important. If you make a wrong choice at this first level, then this will affect all the next design choices, and then you probably will not make high quality software. Then, once you have decided the high level structure for your system, then try to incrementally and gradually work down to the detailed decision. Okay, how about low-level construct? Just as we did the previous slide, we started with an architectural choice. So should we go for monolithic or client-side, client-server architecture? And then once we made our choice, we went down, okay, to the low-level constructs. Then finally arrive at the detailed decisions, such as what's the format of particular data items, what is the individual algorithm that will be used. But these are really the last choice that you have to make. Okay, start from the structure, which is very important, and then go down to the bottom. On the other hand, bottom-up design starts from the bottom, okay? And then here you start making the decision about the reusable low-level module. I mean, for example, you already have a lot of modules already implemented, and then you want to reuse all of them in order to save time and money. And then, of course, if this is your high priority, you need to start from say, okay, what I have, how can reuse them in order to build up my application? Well, this sounds more like a Lego game, where you start from small bricks, white bricks, yellow bricks, blue bricks, different shapes of bricks, and then you compose these bricks together in order to make big buildings or big worlds. Okay, this is and then once you have this set of colorful bricks, then you decide how you put them together in order to create a high-level constructs. Okay, you can make you use many different bricks to make a wall, and then you 3 different walls, 4 different walls, you make room, and so on and so forth. But then, what I suggest is always to have a mix of top-down and bottom-up approach. I mean, if you have a top-down approach, it's very difficult to reuse things, because you might arrive somewhere when you say, okay, I cannot reuse a module that I already implemented because my previous design choices brought me to a different path, for example. But on the other way around, if you start from a bottom-up design, say, okay, let me compose my bricks together, and then you can reach a certain point where you say, oh wow, I cannot reach the quality that I was supposed to achieve because I made a wrong choice later on, before. Okay, so then the very good approach is the mixed one. Okay, you start top-down designing in order to give the system a good structure. Okay, start thinking about what is the good type of architecture that we need in order to accomplish a given quality. And then once we have this structure, then we can start thinking how to fit the modules that we already have into the big picture. Okay, that's what I mean, best practices suggest. Okay, always have a mixed top-down and bottom-up approach. Of course, if you don't have any module to reuse, so go for the bottom-up. Okay, for the top-down. Sorry, you don't need anything to reuse, so you don't need to struggle with this mixed approach. So we mentioned about principles. Okay, there are many different principles that allow us to achieve our goal, and our goal is having a good design. A good design is needed because this can increase the profit by reducing the cost. Okay, remember then one of the most costly activity in the software development process is maintainability. So if you provide a good design to your software, you will improve the maintainability. Improving maintainability means increasing profit and also reducing the cost of maintaining the software, fixing bugs, providing new functionalities, and make changes in the software itself in order to satisfy new requirements. In fact, this also will ensure that we conform with the requirements. Okay, if you have a clear design, it's very easy with the set of functionalities provided by a given module. It's very easy then to compare the software developed with the set of requirements have been stated in the requirement engineering phase. This can accelerate the development because, I mean, once you have a design document which clearly state all the design choices that has been made, then well, the developers can easily follow the design and implement and develop the system itself. And this also allow us to increase a lot of qualities. I mean, there are principles leading to having good usability, efficiency, some others for very good for reliability, some others very good for maintainability and reusability. Well, as always in life, one solution cannot solve all the problems. Okay, every single problem has a specific solution. A specific solution might have some cons and pro with respect to the problem we want to solve. Then we need to find a good trade-off. Okay, some principle might lead you to have a high efficiency but a very poor maintainability. Some others can lead you to have very good reusability but very bad efficiency or reliability and so on and so forth. Okay, so qualities might clash each other. Then it's up to us as a designer to find out a good trade-off between them. Okay, so let's have a small break now, and then we go further with the and start discussing what are these design principles, and then we will discuss well some of them. Okay, see you in a while. Okay, guys. So let's start again. We have a lot of things to discuss, and time flies. So we say design principles. So let's discuss about some of these design principles that we can and should use while designing our software. That's something like something that we really need to take at hand and use every time. Okay, they are very good design principles. First design principle is divide and conquer. That's something that we already introduced before. So trying to deal with something big at once is very much difficult and harder than dealing with a small problem. So first principle is always to understand what is the software architecture that we want to provide to our problem. So get the big problem, split the big problem into smaller problems, and then face every single small problem in isolation. So if we are able to divide and conquer the big problem, we are able to easily find a solution. Okay, and this also has many other benefits. For example, we can separate people. We can create small teams, and each team can face a specific sub-problem. Okay, each individual subsystem is much smaller, okay, than having a huge system. Okay, so we mentioned about the monolithic option. Well, monolithic option is 90% bad solution, okay, nowadays. So monolithic means that you have a huge amount of modules really correlated, highly correlated each other. Okay, this means not very good design choice. Okay, then try to always avoid the monolithic. So, but we will discuss this when we will talk about software architecture. So dividing and conquering means that you can divide the big system into smaller system, and then designing, implementing a small system is much easier than implementing the big one. So these modules or subsystems can be easily replaced or changed without having to replace or change all the system. Well, this is true if the next principles are fulfilled. Okay, that's not true in general. You need to divide the system into smaller subsystems, but this is not enough. Okay, so principle 2. A subsystem or a module that you just created by splitting the big problem into small problem must have high cohesion. Okay, and high cohesion means keeping all together the things that are related to each other. For example, all the set of classes that you use for providing a given functionality, and keeps out other things. I mean, if you have one class which is not closely related to a specific functionality, then you have to put it in another package. Okay, if we talk in the Java language. Okay, this will allow you to make the system easier to understand and change. Okay, so then whenever you looking for a specific functionality, then you look at specific package, and then you already know that within that package there are all the classes that you need in order to provide a given functionality. So there are many different types of cohesion. Functional, as just used as an example. So all the code that computes a particular functionality or particular results is kept together, for example, in a package, as we are Java programmers. Can be layer cohesion. That means all the facilities for providing a set of related services are kept together. Okay, not only one. I mean, you know, in Java you might have packages into packages. Then you can divide, you can have one package for, I mean, all the functionalities, all the services, and then one package for every single service. Can be communicational. It means that all the modules that access a specific type of data, okay? Still, you might, in Java, you might have a package containing all the classes needed in order to compute a specific or processing a specific type of data. Procedural, procedures or methods, as we are still Java programmers, that are used one after another, okay, in order to compute some specific result, or just temporal, okay, all the operations that are performed during the same phase of the execution of the program, okay. That's up to you. What I suggest is to use layer and functional type of cohesion when you split your system, okay? Because this will also allow you to achieve other principles. For example, coupling. That's another really fundamental design principle, very important for achieving modularity, analyzability, and reusability that we discussed before. And that's something that we will discuss deeper on next lectures. Okay, so coupling. What is coupling? First of all, coupling occurs when there are when you have many dependencies between one module and another. Okay, if a dependency exists, changes in one module have can affect and have an impact on the other module. For example, you have two classes, then you have a class A that is using some methods from class B. Then whenever you change the method in the class B, then you also need to change the class A, because otherwise you cannot compile your code anymore. Okay, well, this is coupling. And then if you have a huge amount of dependencies, okay, your system is very hard to understand and hard to modify. I mean, in this example, whenever you touch one of these modules, then you have to change all the other modules as well, because the change that you made in one module can affect and have an impact on all the others. Okay, then, so what we want to have is a low coupling. Okay, so have a less number of dependency as possible. And then here we are talking, these squares can be single classes, but can also be a package. Okay, then, so we will discuss about these during the next lectures. We will discuss about coupling in the architecture, when these boxes will represent a module, but also we will talk about coupling in terms of classes, okay, when these dependencies are in the code, okay, in between classes. There might have also here many different types of coupling, and then we should try to reduce all of them. Can be coupling in terms of content, so when you have one module that modifies data, and this data is used or is internal to another module. Okay, then this can be when you just change the internal variable of another module of another class. It can be a routing call when you use and call methods that are implemented by another class. But this happen in most of the cases. Of course, you always have a need to interact with another class and call his methods. Type that you use when a module uses a data type defined in another module. Okay, and this can be, for example, when you use a class which is defined in a specific package outside the package that you are in. Can be inclusion or import when the module imports a package, for example, as in Java, then you import all the different classes of a package. Can be external when the module has a dependency on such things as, for example, operating system. You might, for example, when you use some services provided by the operating system itself, or a shared library, or the hardware, for example. Then the keyboard, or the screen, or your printer, or whatever hardware you have attached to your computer. Then, design principle 4, keep the level of abstraction as high as possible. That's very important because allow us to ensure that the design can be reusable. Okay, and in order to do that, we need to hide or defer consideration of details. Okay, I mean, talking in terms of object-oriented programming, this means information hiding. Okay, then you need to keep private to the class all that all the internal data. Okay, and then once you have abstractions, this abstraction allow you to understand the essence of the subsystem without having to know the details. I mean, you just need the interface of your class. You don't need to understand how the data or how the methods work. Okay, then information hiding is very important. Two things, information hiding, and as we will see in next lecture, also interfaces. Okay, in Java, interface is a way for increasing the level of abstraction. You make an interface where you declare all the methods provided by the class itself, and you defer the implementation of these methods to the concrete class implementing the interface. I mean, from an external point of view, I really don't care how a specific method is implemented. What I care is the set of parameters the methods get in input and the type of output it provides to me. Okay, we don't need anything else. That's why information hiding is very important. Then abstraction and classes. So usually classes are data abstraction. Okay. We have a class, and every single class in an object-oriented programming define a type of data, and its methods define the different activities, the actions that we can perform on such a type. Okay. Then abstraction is increased a lot if you define all variables as private. I really don't care how a queue or is implemented as a list, or is implemented by using an array, or is implemented by using a database. I mean, I really don't care about you implement a list or how you implement a stack. What I'm interested in is the type of operation I can perform over the stack and the type of result that I get from it. Okay, so all variables must be private, and the fewer public methods in the class, the better the abstraction. Okay, don't try to avoid classes with too many methods declared on it. Okay. If you have very big classes with a lot of methods declared in it, well, this can be a sign that you have a bad mistake, a bad design. Okay, try to split huge classes into different small classes. As we will discuss next lectures, one important things we need to take in mind is that every single class or every single module should have a single responsibility. Okay, so define classes that have only one reason to exist. If they touch a specific data or they provide a specific a small set of functionality. Okay, but we will come back on these next lectures. Then having superclasses and interfaces increase the level of abstraction. Okay, then you can reuse subclasses to make more defined and refined version of your class. And the interface, as I said before, is very important. Remember that also attributes and association are data abstraction, then keep using them. Methods are procedural abstraction. Then better abstraction are achieved by giving methods fewer parameters. If you have too many parameters in one method, is also a sign that the design is bad, because having many parameters increase the coupling, for example, and then this means that you are relying on many different classes from your class, and then it's not very good. Then design 5. Design principle 5, increase the reusability where possible. I said before, reusability is not something that happened by chance. Okay, reusability must be designed. Okay, then design the various aspects of your system so that they can be used again in other contexts. Okay, and this is called design for reuse. So your assets are reusable if you made them reusable. How do that? Try to generalize your design as much as possible. I mean, if you create a class, don't create a class called student, which has all the attributes for a specific user, student. Otherwise, if you do that, you cannot reuse this class in a different project. Okay, then try to give a name and attribute to this class for a generic user. Okay, so the class should be user, not student. So you can reuse this user class in many different aspects, in many different application domain. It can be the university, and then you will instantiate the class as a student, but you can reuse it also, I don't know, for a bank, and then the user would be the bank customer, for example. Okay, then in order to be reusable, it must be generic enough. Also here, we have to find out a good trade-off. Of course, there are no classes that are too much generic are not good, are as classes that are too much specific. Okay, we need to find out a good balance. That's the challenge. Okay, so try to keep in mind we have to create a design which is reusable, but while doing this, keep in mind also that too much generic is not good as well, too much specific. And how to do that? Well, keep in mind the preceding design principle. Okay, try to always increase the cohesion for your class or package or module. Try to reduce the coupling, because the less the coupling, the easier is to reuse the asset. And trying to increase the abstraction will also allow you to reuse the reusability. Another important thing, try to design your system in order to contain hooks. Well, hooks are in Java can be interface. Okay, so always make a massive use of interfaces. Yeah, that's also something that we're going to discuss when we will see we will talk about inversion, dependency inversion. Okay, next lecture. But that's important. So try to use as much as possible of make use as much as possible of interfaces. And try to simplify the design as much as possible. Okay, this is a bit blurry. What does it mean, simplify your design as much as possible? Well, can mean many different things. So as I said before, don't implement a class that has 1,000 different methods. Okay, but it's better to have 1,000 classes with only one method each, instead of one big classes with too many methods. Try to define classes that only touch a specific type of data, okay, and so on and so forth. Keep it as simple as possible. And then the other face of the medal. So on the other hand, we have design with reuse. So once we have reusable assets, so let's use them in order to create our design. Okay. Beware that reusing does not mean copy pasting your code. Okay, so cloning is not a form of reuse. So a form of reuse is that you define your class, you compile your class, and then you reuse the compiled version of your class. Okay, as you use the string class provided by Java, you don't have the source code. You only have the bytecode. Okay, then you are using a class defined by someone else. Okay, that's reuse. Copy pasting your source code from one class to another class is not a good way of reusing your assets. Okay, so that's very important. Then design 7, design for flexibility. So try to anticipate the change, okay, so that the design might have in the future, okay, and be prepared to face these changes, because they will happen sooner or later. In order to do that, you must reduce the coupling, increase the cohesion. That's a very, very important. Create abstractions, and in particular have interfaces. Okay, so try to hide all your implementation behind interfaces, and do not hardcode anything, because if you hardcode anything and then you want to make change to that, I mean, you need to, well, recompile everything. Okay, so try to avoid this. So you can use configuration files. So you can put everything as a variable, but do not hardcore anything, unless you are sure that something will never change. I mean, if you want to have a constant variable defining pi, okay, that's fine. So pi will never change. It's always 3.14 blah 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 blah. Okay, but I mean, these are specific cases. Okay, if you have I mean, try to avoid using constants, and then put constants in an external configuration file. That, I mean, tomorrow you want to change your constant, then you just need to change the configuration file. You don't need to change your code and recompile everything. Try to leave all options open. Okay, do not restrict the option of people who have to modify the system later. Okay, I mean, you are working on the system today. Tomorrow you might change your work, or you might change and work on a different project, and then you never know who's coming after you and work on the system that you are creating today. Okay, so try to don't prevent and restrict the option to these people. Use reusable code and make your code reusable. That's very important. Okay. Principle 8, anticipate the obsolescence. So plan for changes, okay, in technology or environment, so the software will continue to run or can be easily changed. I mean, we are using Windows 10 today, but tomorrow will be Windows 11, and then we need to accommodate this change. Otherwise, our software will not work anymore. So try to avoid using early release of any technology, because usually they are not stable, okay, and then they will change faster, and then you have to change fast accordingly. Okay, so try to always use well-established and stable technology. But Even better, stable technology provided by big players. I mean, you can trust Google to some extent. Okay, Google is there today, and most probably will be there tomorrow. But if you want to use technology implemented by a new startup, well, you never know. The startup can be there today and being very successful, but tomorrow you don't know. Okay, so try always to use well-established and stable technology, where technology can be software, hardware, or whatever. Okay. Try to avoid using software libraries that are too much specific to a particular environment. Okay, for example, a library that only work in Windows 8. Okay, otherwise now, I mean, you could not use it anymore. Then it should be libraries that are, portable, let's say. Try to avoid undocumented feature or little used feature of software libraries, because most probably they will not be maintained. Okay, I mean, if a feature is not used by or is used by few people, then as a maintainer, I'm not interested in maintaining that feature. I prefer to put my effort, my money into features that are used by many people, because this means more profit for me. Okay. For example, there are many services provided by Google a few years ago that nowadays are not there anymore. Okay, so also Google makes some choices. Okay, they go forward with some products and then they drop other products that were not so successful within the users. Try to avoid software or special hardware for companies that are less likely to provide long-term support. That's it. I mean, you can trust Google, but you never know if you can trust a small company that started up their business today. Okay, you don't know if tomorrow they will be still there, and then they will be able to provide you long-term support. And try to use standard languages and technologies that are supported by multiple vendors. So in that case, if a vendor will go out of business, then you can replace this vendor with another vendor. Okay, very easy. Then design 9. Okay, I have to speed up. Try to have the software run on as many platforms as possible. Okay, so in that case you can outreach more customers, and I mean, you don't struggle with specific technologies. For example, avoid the use of facilities that are specific to only one particular environment. For example, only for Windows, or only for Linux, or only for Mac OS if you are Apple customers. Design for testability. I mean, that's very important. I mean, your design should be easy to test. Okay, so try to make and design and make a program to be automatically tested. Okay, and if we talk about Java, we talk about unit test. Okay, as you should already know from previous courses. Okay, whenever you make a class, try to use unit test and make the class testable, automatically testable. So if you have to test again all your code because you made a small change in one classes, then it will be automatic and very fast. And then try to design defensively. That's very important. So never trust, okay, how other developers will use or try to use the module that you are designing. Okay, so if you are designing a module and providing a method that gets two integers as input and make a division, so don't trust so people that will use this module. Okay, make sure that they don't divide by 0. Okay, so try to use as much as possible try catch statements and then use exceptions and try to avoid all misbehaviors. Okay, try to handle all cases where other code might attempt to use your module inappropriately. What means? Check all the inputs and check that these inputs are valid. Okay, this is called precondition. For example, yeah, I say that you don't divide by 0, for example, because someone just provide you wrong input parameter. So some techniques now for just for closing this session. How to make a good design decision? Well, start always from the requirements and use the requirements to make priorities, okay, and objectives. Then list and describe all the alternatives that you have among you have to choose. It's very important. List and describe all the alternatives, and then you can list for each alternatives all the advantages and disadvantages. Okay, with respect to the objectives and the priorities that are being stated in the requirements. Then start from the requirements. That always your starting point. Then list all the possible alternatives and try to write down the advantages and disadvantages of these alternatives with respect to the objectives and priorities, of course. Then 3, determine whether any of the alternatives prevents you from meeting one or more objectives. If you remember the design space and the design path that we discussed earlier today. Then, if you have one alternative that prevents you to go down in the tree and reach your destination, then you have to avoid, okay, that branch or that path. Then choose the alternative that helps you to best meet your objectives. Okay, meeting the objectives is not enough. You need to best meet the objectives, and that's where you have a good design. And then try to adjust priorities for subsequent decision making. Okay, as we said before, so having a journey within the design space is a step-by-step decision-making process. Okay, then whenever we make a decision, let's to adjust the priorities for next steps. Okay, and that's all for this. Before moving on, because I have another small slide set that I want to show you, which is very important. Are there any questions so far? You can write on Slack, okay, if you have any questions, so I can answer you. Otherwise, I go further. I want to show you, it's very important, is within this module, we're going to use this Sonar Graph Explorer tool. Okay, and then there are a few slides here that I want to give you an overview of what this tool is and how to install it. Okay, it's very important that you follow my instructions. Okay, step by step. If you don't, you will, if you will reach a destination which is different than the one that I want want you to reach, and then we might have problem. Okay, we're going to use this tool within next lectures, and you will use it for the assignment. Okay, then it's very important that you listen to me starting from today, okay, because I show you how to install this tool step by step. Okay, so first of all, what is Sonar Graph Explorer? So Sonar Graph Explorer is a static analysis tool that is able to analyze your source code and provide you some metrics. Metrics about the quality of your code, and how it also allows you to visualize all the different dependencies that you have in your code. And as we said, dependencies are very important, okay? Because it is allow us to understand if we have low coupling or high coupling. And also we try to understand if we have a high cohesion or a low cohesion. The tool will allow you also to run some metrics, and we will discuss about metrics in the next coming lectures, okay? It's very important. You will download, I mean, there are different type of sonar graphs, okay, as you can see in the figure. There is a sonar graph product family that is composed by Sonar Graph Explorer, Architect, Developer, Build Explorer, Build Architect. It's very important that you download the Explorer one, okay? The Explorer one is for free for us working at university, and provides you all and only those functionalities needed for running this course. Okay, so last year students that didn't follow this instruction, they downloaded the Architect one. Then they had many problems in accomplishing the assignment. Okay, because my assumption on making the assignment was that they were using the Explorer, but they were using the Architect, and then it was a chaos. Okay, then it's very important that you follow this instruction and you download and install the Explorer, not the Architect or any other of these options. Okay. So Sonar Graph Explorer allows you to visualize the dependencies that you have in your code base. Display, it will allow you to display all the dependencies between the different elements as a layered graph. Okay, then we will discuss how to use this in this course, and allow you also to visualize if you have any cyclic dependency within your code base. As we will discuss next lecture, cyclic dependencies is evil. Okay, it's something that we need to avoid. It's very important to avoid. And also Sonar Explorer will allow you to run some basic metrics. These are code and quality metrics that allow you to assess the technical quality of the software that you are producing. Okay. As we said earlier in this course, there's no quality attribute, there's not quality level if we cannot measure the level of quality. Okay? In order to measure the quality and the level of quality, we need to establish some metrics, okay, so that we can say if a level of quality is better or worse than another level of quality. And then we, using both dependency visualization and metrics, allow us to better understand the software, okay, that we are working on and involved with, even if we don't have documentation. So just running and using this tool on our code base will be enough. So let's get started. First of all, go to this website, hellotomorrow.com, and register. Okay, click on the register button and then fill up the form. And be sure to check a relevant programming language as Java. Okay. Once you registered, just log in. Okay, that's the second step. When you are logged in, you should face this page. Okay, Software Architects Love Sonar Graph. And then you need to click here on this link, which is a Sonar Graph Explorer. Okay, and then you will be redirected to a new page. And be sure you are under the Explorer tab. Okay. If you are under the Explorer tab, then it's red. Then scroll down until the end of the page. When you reach this sentence written on the web page, and then click on download. Okay? Then a new page will appear, and then you have different type of Explorer. Still, again, make sure you read Explorer under the comments column, okay? And then you can pick the version that you prefer. You have Windows or Mac or Linux. Download the one you prefer according to your operating system. So once you download everything, come back to the previous page and click on request your free license. Okay? Follow the instructions and then run the Sonar Graph Explorer and try it. Okay? It will appear empty. As you can see from this image, it's very important that you read Sonar Graph Explorer here in the bar. Okay, and once you have this installed, then go to my Moodle and check the video tutorial and that I uploaded. It's a video tutorial. It's about 14 minutes long. And he will explain you step by step how to use this Sonar Graph tool with an example. Okay, it's very easy. You will be able to manage it in 20 minutes, no more. I also uploaded on my Moodle other tutorials and manuals, and I mean all the information you need in order to use this tool is already there. Then we will use the tool during next lectures to visualize the architecture, the structure for software, the software system that we are developing, and to make measurements in order to understand what is the quality of the software that we are producing. Okay, that's all for today. I hope you could listen and understand everything. If you didn't, please send me make questions or send me an email. Still, it's very important you follow this set of instructions step by step, okay? Because as said last year, some students didn't do that, and then they messed up with the assignment, because the assignment is so the assumption that I have in the assignments is that you are using the Explorer version of this software. Okay, I mean, don't download the Architect version just because it has more feature. Yes, it has more. It provides more features, but we don't need those features for this course. Then you might download and install the Architect version later on after you passed the course. Is that okay? Okay guys, that's all for today, and then we meet again on Friday. Bye bye.